actually interacting, learning this course through online mode, which is not really touchy until unless we visit the lab, okay? So the lab part is missing. So what we have tried actually, can we show something related to the laboratory deployments and experimentation? So this is your first experimentation where we will run actually two videos today. One is actually for wind and the other is for the PV. And if you're all ready, please concentrate, have your pen and paper, and the video is before you. We are just about to start.
Very good morning.
Sound?
Welcome, dear
Are you
student
audible?
friends. And today we are going to focus on
Please let me know if you all are audible. All are audible? Very good.
Smart Grid, Basic
Sound
to
better?
Advanced Technology, Module 9, Lecture 1. And the main agenda today is to focus on demonstration of solar power generation. I request all of you to concentrate and let us not be in hurry and make sure that you complete the full module in one go for better understanding. The test bed which we are going to use for the demonstration of solar generation, I wish to highlight here the DC power from the PV panel is converted to AC power through the Poltronic interface, which is basically called as inverter. The solar inverter can operate either in grid connected mode, also called utility mode, or islanded mode can also be popularly known as standalone mode operation. And in this course, only the hardware demonstration of grid connected mode of solar inverter is considered. As per the grid codes, the inverter operating in grid connected mode is expected to inject high quality currents followed by providing grid support standards. Now, when you look into the hardware setup of a single stage inverter and its control system, resembles the one in this schematic slide. The single stage solar inverter is represented here along with its control system. It has all the control loops such as the MPPT loop, inner current loops and grid synchronization loop, which is essential to solar inverter operation. Let us see more details on the inverter connections and its control in the coming slides. Let us focus on the test bed description. The test bed which we are going to use for the demonstration of solar generation, the components of the test bed are programmable DC source which can emulate the characteristic of PV panel, and the next one is the grid emulator which acts as an interface to connect the inverter to the grid. The grid emulator takes the power from the inverter and feed it to the distribution system. Now, the next component is semicron IGBT stack, which acts as inverter and performs the single stage power conversion from the PV emulator to the grid. Now, we have the voltage and current sensor circuit boards along with signal conditioning circuits, and for the test bed the control system is implemented in the Opal RT platform. An inverter which is controlled by using Texas DSP will also be demonstrated in the upcoming lectures. We have an MCB which forms the PCC to connect and disconnect the inverter from the grid. Now, let us see the details of these test bed components. To start with, let us focus on programmable DC source. The rating of the model that we are using for our demonstration has a power rating of 5 kilowatt and a voltage rating of 600 volts. It is basically a single channel one. It is directly connected to the DC bus of the 3-phase inverter in our test bed. Now, when you focus on the characteristic of a solar cell, I mean, we have used an emulator which allows us to set the maximum power point voltage, maximum power point current, open circuit voltage, PV power, and so and so, thereby emulating the PV and IV characteristic of a solar cell or array as shown in the slide. It is the duty of the inverter to track the maximum power point by delivering power to the grid. Semicron IGBT stack, we can see here in the video, we have shown a single IGBT stack which has semicron switches and diodes. Before talking about the rating of the IGBT stack, let us look into the circuit diagram of the stack. It mainly consists of two sections. One is the three-phase diode bridge rectifier towards the left, and in the right it is the three-phase four-wire inverter bridge circuit. The three-phase diode bridge rectifier has the input AC voltage rating of 415 volt and DC output voltage of the rating 560 volts. The inverter bridge has DC input voltage rating of 700 volt and AC output voltage rating of 415 volt RMS along with 30 ampere output current. One important thing to be noticed here is that the DC input capacitor or the DC bus should be rated to more than peak of the grid voltage such that the power can be transferred from the DC side to the AC side. The basic understanding here that until unless you create a voltage difference, it is not possible to transfer reasonable amount of power from one point to the other. For 415 volt RMS AC grid, peak voltage is around 586 volt and the rating of the DC bus is 700 volt. This ensures that there is a sufficient margin for the inverter operation, and in our demonstration we kept higher operating margin by considering the maximum DC bus voltage of 400 volt DC and 110 volt RMS AC grid. The IGBT module used here is SKM75GB12T4. You can see here we have an IGBT module shown in the video, where in terms of the rating it is not same as the one used in the IGBT stack, but physically it look quite similar. Here one module can form an inverter leg, as each module consists of two IGBTs along with the corresponding body diodes. Hence, four such modules are used to form a four-leg inverter. The rating of the IGBT module used in the stack can block voltage up to 1200 volts and also can carry a nominal load current of 75 amperes. It supports switching frequency up to 20 kilohertz. These modules are attached to the aluminum heat sink, which can be seen here to dissipate the heat. These IGBT modules are popularly used in solar inverters, motor drives, as well as UPS applications. Within the stack, forced air cooling through fan is also provided for carrying out fast cooling. Also, in the inverter section, one can notice that each IGBT module is provided with the snubber capacitors, those are connected in parallel to provide protection against the high dB upon dt. The trigger that IGBT switches gate drivers are required to convey the pulses received from controller to the gate terminal of the IGBT. Each driver can trigger one module, hence 4 numbers of Skyper 32R gate drivers are provided. And these drivers also require isolated DC input of plus or minus 15 volt to operate. Moreover, these drivers have inbuilt dead band protection as well. At the DC link input of the inverter bridge, we have earlier seen 2 semicron make electrolytic capacitors are connected in series whose ratings are 4700 microfarad, 700 volt each. Across each capacitor, bladder resistors are connected to discharge the stored energy in the capacitors when the inverter is not in operation. Apart from this, the IGBT module also has an inbuilt thermal trip protection feature in case if device exceed the threshold temperature. There are 4 legs in the inverter. For our application, we are using only 3 legs because we are demonstrating solar generation for balanced 3-phase 3-wire system. Moreover, we are talking about only the single stage conversion. It is also possible to use the same setup for 2-stage conversion as well. The leftover 4th leg can be used to build the DC-DC boost stage. And how can we do that? Let us understand in detail. Let us say we have 4-leg inverter so that the legs consisting of R, Y and B phases are utilized to rig up 3-phase 3-wire inverter, and this will be the DC-AC stage. Now, to build DC-DC stage, we can use the unused 4th leg as mentioned earlier in my previous description. And currently we can see the actual DC-DC boost converter circuit which has been shown here, and how to build using this IGBT stack along with the DC-DC inverter. We can connect positive terminal of PV input to an external high frequency inductor whose other end is connected to the point N. The lower side IGBT T2 can be used as switch which is connected between point N and DC bus negative. The body diode of IGBT T1 can be used as diode for the freewheeling action when T2 turns off. Then the cathode of this diode is connected to the DC bus capacitors. This is how we can build DC-DC stage as well as DC-AC stage using a single IGBT stack. Now, let us move to the test bed understanding. Next component of our test bed is the voltage and current sensor circuit. We use Hall effect based sensors for both voltage and current sensing. LEM make voltage transducer. LV25P is used for voltage sensing, while the current transducer LA55P is used for current measurement. Also, the circuit board has plus or minus 12 volt DC power supply circuit to power up the ICs present in the sensor board. Apart from these LEM sensors, the sensor circuit for voltage and current measurement also consists of signal, conditioning circuit and level shifting circuits. Now, moving to the component of the test bed which is quite important, so called Opel RT. The control system of the inverter is implemented in Opel RT, which runs on RTLab software by calling the MATLAB Simulink files. Opel RT is basically a real-time simulator which can be used to perform real-time simulation using MATLAB / Simulink as well as performing rapid control prototyping by implementing the power electronic converter control. First, we can simulate the system in MATLAB Simulink. Later, remove the plant from the simulation file retaining the control system, then implement the plant using real hardware and finally call the simulation file with the inverter control from RTLab. To perform rapid control prototyping, we need to access the analog input output pins, which we generally call them as analog input outputs. The model of Opel RT that we are using is OP5700. In the video, we can see 16 analog inputs, 16 analog outputs, 32 digital inputs and 32 digital outputs. The output and input voltage range of analog pins is plus or minus 16 volts. Accordingly, the voltage and current sensor circuits are designed such that their output voltage range is not exceeding the voltage range of analog input pins of the Opel RT under any circumstances. The PWM pulses generated from the control system can be taken out of the digital output pins with magnitude of either plus 5 volt or plus 12 volt by connecting an external DC source to the specific pins of the digital out. Now, the next attempt is to sense and PWM outputs. Using these analog input pins, we can send the 3-phase voltage and current signals sensed using sensor circuit to the control system. So, we need at least 3 input pin for AC voltage and 1 for the DC voltage, 3 pins of AC current and 1 pin for the DC current sensing. In total, we will be using 8 analog input pins. Similarly, the PWM pulses generated by the control system need to be taken out of the digital output pins of the Opel RT. Now, these level shifted PWM pulses which are generated in the order, the digital output pins 1 to 6 gives PWM pulses. Digital output pins 1 and 2 generate complementary pulses for the IGBT module of the R phase. So, these output pins 1 and 2 are connected to the input pins of the Skyper 32R gate driver, which is dedicated to the R phase of the IGBT module. Similarly, the digital output pins 3, 4 and 5, 6 are connected to the respective gate driver of that phase. These gate pulses are of 0 to 12 volt magnitude with respect to a common potential, external DC source negative in our case. However, the gate terminal of IGBT requires positive and negative voltage to turn on and turn off the device. For this, we can utilize the plus minus 15 volt DC power supply board present in the voltage and current sensor board. Therefore, each Skyper 32R driver has 5 inputs. 2 inputs are dedicated for PWM pulses, one for top switch and the other for bottom switch. Next 2 inputs are plus or minus 15 volt DC supply, and one input is the common point of the plus or minus 15 volt DC supply. This holds good for the other 2 phases as well. Now, we will see what kind of control loops are programmed in the Opal RT to control the inverter. We all know that solar inverter works with 2 configurations commonly. One is single stage conversion, while the other is dual stage conversion. In single stage conversion, PV panels are directly connected to the inverter DC bus, as there is only one conversion stage. The device switching and conduction losses are quite less. This results in improved efficiency and reduced cost. In case of a dual stage conversion, first there will be a DC-DC stage to extract maximum power, followed by DC-AC stage. For single stage conversion, the control system is shown here in the given slide, which consists of an MPPT stage followed by DC link voltage control and current or power control loops. Apart from these loops, grid synchronization loop using phase locked looped so called PLL helps in synchronizing inverter with the grid voltage before feeding power to the grid. This MPPT block gives the DC link voltage reference so called VDC link star. The DC link voltage control tracks the voltage reference by providing the current reference ID star. The innermost current loop tracks the reference current to deliver the maximum power. Note that the control system is implemented in DQ frame with synchronous reference frame of the PLL. Here ID star represents the D axis reference current, which will control the active power. Similarly, we can control the reactive power injected to the grid so as to provide voltage support by tracking the reactive power reference QAC star. In the dual stage conversion, DC-DC stage has MPPT block, PV voltage control and current control loops, while the DC-AC stage resembles the one in single stage conversion, but here in this demonstration our focus will be on single stage conversion only. Now moving to the hardware demonstration. Now before going into the demonstration, let us have a look at the hardware connections. The PV emulator is connected to the DC input terminals of the IGBT stack. The AC output terminals, that is RYB phases, are connected to the L filter. For each phase, we have connected 2 such inductor boxes in series to form total inductance per phase 6 millihenry. The other ends of the inductors is connected to the point of common coupling PCC formed by this MCB. At this MCB connection, bulb loads are connected in parallel path and they act as a load. The other side of the MCB is connected to the output side of the grid emulator, while the input side of the emulator is connected to the distribution system of the campus. Also, notice that after inductors, the wires are passed through the LEM current sensors. For voltage measurements, sensing is done near MCB input and the sensed signals are connected to the LEM voltage sensor board. The setup is ready for demonstration. The control loop is enabled, the synchronization to the grid voltage is ensured by the PLL. The MPPT and DC link loop will track the maximum power giving the reference current, and the current control loop will further track the reference current. So, in this way maximum power point is getting tracked. We can see the 3-phase inverter output current waveforms are captured in the DSO. The current that we are seeing is fed to the distribution grid via grid emulator. Now, the irradiance is varied in steps and the corresponding inverter output currents are captured in the DSO. Thank you very much. Very good morning, dear student friends. Today we are going to discuss on demonstration of wind power generation of the course titled Smart Grid Basics to Advanced Technologies. Now we are going to discuss on a test bed for the demonstration of wind power generation, and as you could see, this is the brief introduction to wind power generation. Ideally, we capture the kinetic energy through wind turbines and through gearbox to the generator and through power converter to the transformer, and hence the energy is being fed to the power grid. A typical wind power generation convert kinetic energy of the wind to the useful electrical energy. The aerodynamic modeling equations of the wind turbine helps to access the performance of the wind turbine with respect to the varying wind speed. The power generated from the wind turbine is a function of the power coefficient and the wind speed. With the recent development in the semiconductor technology in the field of wind energy, the less productive fixed type wind generators are being replaced by the partially variable and completely variable types. Among the variable type of generators, the DFIG wind system, which is one of the partial variable type, is known for its cost effectiveness due to the scale down in the converter size. The power converters are rated to handle complete range of wind speed variations. Now focusing on doubly fed induction generator, so called as DFIG WPG, the schematic representation of the DFIG wind system along with the power flow is shown in this slide. As the name suggests, the doubly fed induction generator is capable of feeding or observing power in two directions. The stator part is directly exposed to the grid, which works at fixed voltage and frequency. Henceforth, it is mandatory that the stator of the DFIG is compelled to operate as per the grid norms. However, this is only possible if the rotor operates at synchronous speed. In a practical scenario, the speed of the generator keeps on varying from the sub-synchronous speed, say in the morning hours when the wind speed is low, to the super-synchronous speed in night hours when wind speed is extensively high. Thus, with the conventional induction machine, it is not possible to inject power from the wind system to the grid. With the DFIG setup, it is possible to inject power at varied wind speed into the grid via stator over a speed range of plus or minus 30%. During the sub-synchronous mode of operation, since the wind speed is less, the positive slip power is drawn from the grid via rotor side converter, grid side converter, combination to the rotor such that the prescribed power at the grid frequency could be injected from the stator end. By neglecting the losses of the back-to-back converters where Pg equal to Pr, we can say that the power at PCC is equal to the addition of the power generated by the wind turbine, that is the stator power and the rotor power. Here P equal to Ps plus Pg, that is the summation of Ps and Pg. During the sub-synchronous mode of operation, rotor speed is less than synchronous speed and thus the slip is positive. Similarly, during the supersynchronous operation, the excess power from the rotor in terms of negative slip, power flow out from the rotor via RSC and GSC combination, thereby helping to follow the grid norms as per the nominal values. Whereas during the synchronous mode of operation, there is no power injected or observed from the rotor and the entire power flow from the wind system is transferred to the grid via stator itself. In summary, by controlling the RSC and GSC, the DFIG wind system can be made to function in all the three modes of operation. Now, focusing on the hardware demonstration of the setup of wind turbine, grid connected operation of the DFIG setup. Now, before going into the demonstration, let us have a look at the overall hardware connections. DFIG hardware setup consists of three units mainly. The first one is a wind emulator, DFIG, and back-to-back voltage source converter. The laboratory setup of DFIG is basically a slip ring induction machine coupled with DC motor. This DC motor of rating 2.5 kilowatt, 220 volt, 10 ampere, which behaves similar to prime mover and is controlled by chopper control, providing different wind characteristics. For obtaining the wind emulator, the wind characteristics along with the wind turbine action is mimicked with the help of a buck converter. The DC motor output is controlled via armature voltage control, for which the semicron IGBT stack is being used. An inductor and a capacitor is used to form the buck converter. The control strategy for buck converter is as shown in the schematic diagram. Now, the DFIG control, so called wind emulator, it can be noticed that the wind power, which is half of rho A Cp V cube, in the control scheme is calculated by taking input wind velocity and pitch angle. Here the Cp is the power coefficient which is dependent on the pitch angle and tip speed ratio. Further, the wind power is divided with the measured speed of the rotor to generate the reference torque. The motor reference current is obtained by multiplying the torque reference with the motor constant of value K, which is equal to 4.16 in our case. The current reference is then compared with the actual current of the DC motor. The compared result is sent to the PI controller, thereby obtaining the switching pulses. Now, the induction generator of 2.2 kilowatt rated and is operated through the field programmable gate array FPGA based controller. Wavect FPGA controller of firmware version WCU 10081E is used, which is capable of sensing 8 voltages and 8 current signals along with 8 PWM pulses. While the stator of the slip ring induction motor is connected to the power amplifier via a switch, the switch is initially open and is further closed when the stator voltage and phase angle action. Now, focusing on the hardware demonstration of the setup of wind turbine, grid connected operation of the DFIG setup. Now, before going into the demonstration, let us have a look at the overall hardware connections. DFIG hardware setup consists of 3 units mainly. The first one is a wind emulator, DFIG, and back to back voltage source converter. The laboratory setup of DFIG is basically a slip ring induction machine coupled with DC motor. This DC motor of rating 2.5 kilowatt, 220 volt, 10 ampere which behaves similar to prime mover and is controlled by chopper control provide
So, evening everyone. So actually second video part of that batch not completely available. So we are making it correct now. Please stay tuned. We will be back in 2-3 minutes.
Webect FPGA controller of firmware version WCU10081E is used, which is capable of sensing
It's audible to all of you.
voltages.
Let us. It's audible. It's audible to all of you. Video. Yes.
And 8 current signals along with 8 PWM pulses. While the stator of the slip ring induction motor is connected to the power amplifier via a switch, the switch is initially open and is further closed when the stator voltage and phase angle is synchronized with the voltage and phase of the grid and phase angle using the rotor side converter. After synchronization, RSC regulates DFIG to operate in the speed power control mode. Rotor of slip ring induction motor is connected to the RSC, which is controlled in the FPGA platform. Now, if you look into the DFIG control through rotor side, field oriented control FOC established on the vector control is enlisted for D and Q axis control of rotor current. The maximum power point tracking MPPT is implemented using perturb and observe P&O method by estimating MPPT reference rotor speed at particular wind velocity, regulating the Q axis of the rotor current IQ RSC. Now, the D axis part of the rotor current is governed for managing the stator power factor. This is done by introducing reactive power for smooth variation. Further, the reference voltage is converted to the ABC frame to generate the PWM signals, which is fed to the RSC switches. The RSC is connected to GSC via a DC link, and the job of the GSC is to maintain the DC link voltage. Now, looking into grid side control, the generated DC link voltage when compared with the measured voltage of DC link generate error that is processed through PI controller to obtain D axis reference current. The measured GSC current D axis component tracks the reference value with the PI controller to obtain the reference D axis voltage, while the PI controller dealing with the Q axis component of GSC current is assigned to regulate reactive power injection. Now, the software which is available through Webect suite for FPGA controller that run on HDL coder, in this platform we provide the governing variables value. First, we connect the Webect via a LAN cable to the PC and connect the supply voltages. The supply voltage we give by power amplifier of rating 15 kilovolt ampere and 50 hertz. The 3-phase voltage is set in the amplifier 140 volt to get line to line voltage of 240 volts. The grid voltage is reflected in the software due to presence of voltage sensor at that point. The main and the rotor branch circuit breaker is switched on and the DC link is charged initially to 340 volts. Then we enable phase lock loop and check the reference theta with the phase A voltage. Once the DC link is charged, we enable the GSC control to maintain the desired DC link voltage, which is set to say 30 volt greater than DC link voltage, that is close to 380 volts. We see that GSC tracked the DC reference voltage and measured DC link voltage is read as 385 volts. Now, the next step is to enable DC motor control to run the DC motor to provide wind characteristic in the rotation. Here, we vary the duty of the chopper gradually to make the motor run at more than 900 RPM. We are varying the duty and notice that speed is keep on increasing. We can check the rotation here in the speed panel. We see the DC motor is driving the induction machine. Next, we provide the PI value of the rotor side control and enable the control loop. The RSC first is used to build up voltage in the stator side and then match the phase difference of the grid to the stator till they align for the synchronization purpose. Now, we will increase the reference value to match the stator voltage magnitude with the grid voltage using the D-axis control of the rotor. In this process, we also observe that the rotor current is also increased as it takes current from the grid to build the stator voltage, as from the relation the stator power is 1 by slip times the rotor power. I repeat, in this process we also observe that the rotor current is also increased as it takes current from the grid to build the stator voltage, as from the relation the stator power is 1 by slip times the rotor power. The slip is varied plus or minus 30%. So, small current injected to rotor side results in a larger voltage across the stator. Then we vary the Q axis of the RSC to vary the theta. We change the reference till theta is matched. If we see the grid and stator voltage, we see the waveform almost overlap with one another. After voltage get matched in the software, then we check the contactor of the grid side and stator side and ensure that the voltage across the contactor in multimeter is less than 20 volt. Here we are getting a value of less than 10 volt across all three phases. By ensuring voltage is less than the contactor connecting the stator and the grid connection is closed, and then the synchronization is done by enabling sync done in the software simultaneously. Now, the control of RSC is changed from synchronization operation to power speed control mode. Here we see that the 3-phase rotor power is sent. Now, we enter the speed control mode and vary the wind speed to vary the rotor speed. Here we demonstrate the DFIG in 3 different operating modes. Number 1, subsynchronous mode, 2, synchronous mode, and 3, supersynchronous mode. Now, in case of the subsynchronous mode, the rotor angular frequency is lower than the synchronous angular frequency, where omega r is less than omega s. We consider omega s, which is close to 1000 rpm, and the slip is greater than 0. The total power to the grid is 1 minus slip times P stator. The stator delivers power to the grid while the rotor receives power from the grid. Next, we slowly increase the speed and bring it in the synchronous mode. The rotor angular frequency is equal to the synchronous angular frequency, where omega r equal to omega s and the slip which is equal to 0. DC current flows into the rotor winding. The total power to grid is P, which is stator power. Only the stator delivers power to the grid. If we further increase the speed of the DFIG, works in the super synchronous mode. The rotor angular frequency is higher than the synchronous angular frequency, that is omega r is greater than omega s, and hence the slip falls which is less than 0. The total power to the grid is P, which is 1 plus slip time P stator. Now, both the stator and the rotor deliver power to the grid. With this, we have today understood how a DFIG wind turbine operates, and thank you for your attention.
Audible, dear students? Hope I'm audible. Yes, very good. So I think excellent. So what I wanted to highlight today, I think this journey will continue. A couple of times, almost every day, we'll try to have little bit of laboratory experience, which is very important. Because we all know we talked about synchronization in the past. We talked about actually PV energy being extracted. We talked about wind energy being extracted. But the important part, actually, the laboratory development of those experiences, as I mentioned, this belongs to the Admire lab of IIT Roorkee. You can, during free time, you can go admire-lab@iitr.ac.in, where most of the videos actually not available as of now, but we are trying to upload it so that you all can actually refer it. But for the timing, those videos are actually available in YouTube. There is all, I think I'll request Dr. Manmohan to share the link for both the videos, and perhaps you will be also receiving a couple of more videos in future. So please have a look. The step number 1 is read it, go through the video. Actually, you can pause it and you keep on, understanding each and every step. I don't think so anything can be simplified further for better understanding. Well, I tried my level best as simple as it can be, like a, young second year kid in the laboratory and to demonstrate. And I mean, to be very honest, I am really excited, and you all will be very happy to know all these videos are recorded during my MNIT stay. Yeah, these videos are not. Yeah. Actually, they are all. Actually, I used to travel to. This has been recorded after I joined here. Okay, and that's what actually that previously when I came here, the course was actually very simple, basics of fundamentals of smart grid, and then we renamed it as a advanced smart grid basic to advanced technology. So that advancement means basically those serious lab components. So most of the videos that you see is being recorded after joining as a head of the institution of MNIT Jaipur. So this is not a surprise to most of you actually. So I think it is because of your motivation all the time to contribute something. So I silently do something every day, and that is before you today. And you all will be happy to know that there is a course on power system operation control, which has been recorded after I came to Jaipur. There is a course on uh, distribution system analysis, a component, late Professor Ganesh Kumbar, who passed away. So then I wanted that course to continue. So I contributed 20 lectures. And that course is on. And this also happened after I joined in Jaipur. And then one more interesting course, which is distribution system analysis and control, a very advanced distribution system analysis, which is currently under preparation and will be already started. Last week, actually, the course already started. And the registration last date is actually 15th of August. So I request everyone to register all the courses which are running today. That is two courses. One is distribution system analysis and control, as well as distribution system analysis. So both the courses on distribution system, I request everyone to register and give suggestions how this can be improved. So I think all the courses are actually interlinked, and perhaps actually the smart grid course is my, kind of not only brainchild, but also I have a lot of emotional connect to this course. So when we were running, actually, I have simply gone there, actually, the devices, everything was there, but the recording happened actually due course of time. And you will really enjoy more and more when we go further. Okay. We have a couple of more videos also to run in future. So I think all of you please go through both the videos, and then let us know, drop an email to Manmohan, actually, any specific thing need to be repeated or detailed, elaborated. We'll be happy to do that for you. Okay. So with this note, we come to an end today. And thank you very much for your patient listening to the video. And hope tonight you'll be reading again, going through the videos again, making a note. Read it and then write it down. And then that become a Bible for you. Thank you. Both the videos you see.
So I hope everything was live only, so may not be more questions. Anyway, if you have any question, you may ask. The platform is open to you. So, right. So thank you very much, sir. So thank you all for.
We will meet tomorrow again, the same time. Yeah.
So tomorrow we'll have continuation of this course. Thank you.